Right, here it is, all fixed and ready to go. Now with sound, our Unit 3 review. I'm going to try to go through this as quickly as possible so that way you'll be able to get this in before your Unit 3 test. I would suggest that you have paper, pencil, calculator, periodic table, a table of electronegativity to help you as you're going through this Unit 3 review. All right, of course, first, what has the greatest intermolecular force? And hopefully you're thinking that was our solid here. And you're exactly right. That solid is going to have the greatest intermolecular force. And so again, whether something's a solid, a liquid, or a gas, it's a balance between those intermolecular forces and kinetic energy. And so in a solid, our intermolecular forces are much greater than our kinetic energy. Um, uh, and so if we're taking a look at that, which state of matter has a defined shape? Hopefully, once again, you were thinking our solid has that defined shape. And so as we're taking a look and thinking about solids, most of the solids that we have talked about look like the solid pictured here, that sort of regular repeating pattern. So you should, and we call that a crystalline solid. You should be aware that there are other kinds of solids besides crystalline solids. And those would be things like a network solid. Our ionic solid is that crystalline structure. Our molecular solid that has covalent bonds, and metallic solids. All right. And so which one would have the lowest intermolecular force? Of course, that would be our gas. Those gas particles, there would be very little attraction between those particles. And so one of the things that we could also take a look at is how much energy, of course, would it take, would it be required to change it from a solid to a liquid or a liquid to a gas, vice versa. And so you'll want to be thinking about that. And so as we're taking a look at that, one of the terms that we haven't probably used enough is called heat of fusion. And so when we're turning a liquid to a solid or a solid to a liquid, that amount of energy, there would be a certain amount of energy to required to go from a liquid to a solid or a solid to a liquid, and that's called our heat of fusion. And the same thing with the gas. Typically with a gas, it's called latent heat. It's what powers a thunderstorm and lightning. All right, so taking a look at this phase change diagram, you do need to be familiar with that, all the different phases. So ABC, what'd you think? Hopefully you said solid, liquid, gas. You're exactly right. You should have also from A to B, A to C, C to B. What is that process called? Hopefully you said melting, sublimation, and condensation, and you're exactly correct. And so one of the things that we can do is we can calculate that quantity of energy required. And of course, energy is measured in temperature here on our x-axis. And that, don't forget that quantity of heat or of energy is the mass. It can also be times specific heat. And the change in temperature, or it can simply be that heat of fusion. Now the heat of fusion for water is 334. So if we were going to look at the quantity of energy to change it from a solid to a liquid at the melting point, so it's not going to change temperature here. It is just going to change its state. All we need to do is multiply that mass times that heat of fusion for water, and we would get how the quantity of energy. And so energy will keep coming back and back. So we cannot forget, it's like stoichiometry, we cannot forget about how to calculate quantities of energy. All right. How about the intermolecular force? What would be the strongest intermolecular force here? So take a moment, pause the video, see what you can do. Hopefully you said, and of course now I'm going to take my pictures away here, London dispersion for our non-polar molecules, dipole for our polar molecules, and also London dispersion for our non-polar molecules. And if we're looking at something like PCl3, the way we can determine that is by looking at the electronegativity difference. We're coming up with an electronegativity difference of 0.97, so it's greater than 0.5. So it is going to be a polar bond and a polar molecule. The shape allows it to have that polarity as well. And so as we're taking a look at this, we can see that this chlorine end of this molecule is a little bit negative. And the phosphorus end of this molecule is a little bit positive. And so that's why we're going to have that polar molecule. And so the intermolecular force that would hold these molecules together is our dipole force. All right. And of course, don't forget that the temperature of a gas is going to affect the gas. How? And it's going to affect the gas by making the particles move more. Remember, this temperature is measured in kelvins. Kelvins are our scientific temperature scale and tell us about the actual movement of the particles. It's also really good because we're not going to ever have a negative Kelvin temperature. And so how does the temperature affect that gas? It's going to affect it by increasing the pressure. The gas particles are moving more, they're bumping into each other more, they're bumping into the sides of their container more. All right. Gases and STP. Every time you see STP, you should be thinking 0 degrees Celsius, 1 atmosphere of pressure. 22.4 liters of any gas is equal to 1 mole at STP. So if you had 3.3 liters, how many moles would that be? Great time to pause the video. Hopefully you said something just about like this. I'm hoping so. So here is our known quantity. 1 mole of a gas is 22.4 liters. When we multiply it like that, of course, our liters cancel out and we've got moles. All right. Here's a nice little gas stoichiometry. So see what you can do with this one. Well, how did you do? Did you first write this equation? Notice that this equation wasn't balanced, and so add your coefficients to balance it. And then, of course, we're starting with the 28 grams of aluminum, converting that to moles of aluminum, then using our mole ratio. And now that we know how many moles of H2, we can use that 22.4 liters, and we come up with 33.6 liters of hydrogen gas, rounded to 3 significant figures. And I'm hoping that you got that one. Let's try another one. Do you know the gas laws? So take a moment and take a look at each of these and see if you can identify those. All right, so hopefully you said Charles, Gay-Lussac, Avogadro's, Boyle's, and the ideal gas law. So not only do you need to be able to identify them, those laws and the formulas, you need to be able to use them. All right. And now we've got some solution problems. One of the things as you're going through the test is the gas problems are going to be mixed right in along with the solution problems. So what is the molarity of a solution in this case? So great time to pause the video, pull out that periodic table. So hopefully you were thinking, okay, so I've got to calculate molarity here. And I know that molarity is the number of moles divided by the volume in liters. And I just like to look at molarity as moles divided by liters. And so, of course, the first thing that you had to do was convert these grams to moles using our molar mass. And then once you figure out how many moles, just simply divide by the liters. And there you go. A 0.054 molar solution is how we read that word, that concentration. All right, here's another one. So thinking about what formula are you going to use? So the hardest thing about this problem, I feel like, is figuring out the formula. So if it's nickel 2, that's a 2 plus. Sulfate, of course, is a 2 minus. And so you can see that your formula is just going to be NiSO4 because the 2 plus and the 2 minus are going to cancel each other out. And I'm supposed to have the eraser here. I don't know why it's not erasing. But it's not. So that's fine. All right, so what do you say? How many moles would there be? So hopefully you came up with something like this, knowing that your number of moles is your molarity, your big M, times your volume in liters. Notice that these liters are going to cancel out or diagonally drop, so you're left with your moles. All right. So see if you can go ahead and calculate this one. So once again, I'm going to use my molarity formula, my molarity triangle. I'm going to multiply my molarity times my volume, and then I'm going to get my number of moles. And then, of course, I've got to multiply by my molar mass to determine grams. And so if I were going to make this solution, I would just take and weigh out 12 grams of NaOH, dissolve it in a little bit of water. Probably I would use a volumetric flask and then dilute it to 500 milliliters. All right, how about this gas problem? See what you can do. And so once again, I would always suggest that you're memorizing the entire formula. Of course, here, we're not given any information about volume, so I just need pressure and temperature. And of course, you've got to convert your temperatures first to kelvins. And hopefully you came up with 0.7 atm, rounded to one significant figure. And so this change in temperature really wasn't enough to do much to the pressure, obviously, here. All right, let's see what's our next one. All right, solubility. You do need to know these. Temperature, the amount of a solute and solvent, also the type, because remember, like dissolves like, and the size of the particles for a solid are the three factors that affect solubility. Remember, as temperature increases, solids are more soluble, but gases are the opposite. And don't forget that as we're adding a solute to a solvent, the properties of the solvent are going to change. Those are called our colligative properties. All right, make sure you know the solution vocabulary. Go ahead and take a moment and take a look at each one of these. Hopefully you said that the solvent does the dissolving, the solute gets dissolved. Ions produce electrolytes and conduct electricity. When a solution is full of solute, it's called saturated. An aqueous solution has water for its solvent. Water is the universal solvent, and when a solution has more than the maximum amount of solute in it, it is called supersaturated. And here's a little solubility graph so you can see the line. The line represents that maximum amount of solute. In this case, it would be KCl that can be dissolved at a specific temperature in 100 grams of water. And so you could always take a look. So if I had water that was 30 degrees, I could dissolve about 35 grams of KCl per 100 milliliters of water. And that is our saturated solution. All right, talking about solutions. Potatoes, maybe you knew this about that they use a chemical, the NaOH that we've used in the lab, to peel potatoes. So see what you can do with this problem. All right. So hopefully you took those 4 grams first, used your molar mass to figure out that it was 0.1 moles, and divided by your volume in liters to come up with a 0.20 molar solution. Here's another one for you to do. These are solution stoichiometry problems. Great time to pause the video, and then we'll see what we got. So, of course, first, you've always got to write out your formula, make sure it's balanced. And so as I'm looking at this, I can see that I know that I've got 10 milliliters of sulfuric acid, but I've got 15.9 milliliters of my base, which is the KOH, and 0.150 molarity. And so when you know two pieces of information about one of your compounds, I would say start with that one. Then, of course, so I've taken the molarity. Of course, molarity is our moles divided by our liters. And that's going to cancel out. The volume will cancel out. And now that I've got moles of H2SO4, all I'm going to have to do is divide by the volume. Now, in this case, I can divide by my milliliters here. I didn't need to change it to liters, but you might. And then I'm going to get the molarity of the H2SO4. So hopefully you got that same thing. Right, don't forget those intermolecular forces. If a molecule is non-polar, the only thing that would stick it together would be London dispersion forces. If hydrogen is bonded to FO or N, it's hydrogen bonding. All right, here's another gas law problem for you. Great time to pause the video and see what you can do. Of course, this was Dalton's law of partial pressure, and I can see I've got my pressures right here. And I decided to turn them into atmospheres. So I took each of them and divided them by the correct conversion and figured out how many atmospheres there was. Then I took, after I did that and figured out how many ATMs, I simply added them all together and I came up with the total is 1. And I do think I have an extra significant figure here. So that should not be there. So like minus 0.5 points from me. All right. So again, here's an STP problem with a gas. So don't forget what you should know. Great time to pause the video and see what you can do. All right, so hopefully you use those 6.25 liters of helium, and you used your SCP conversion. Then you did your mass, because we were asked for the mass of helium. And so hopefully you came up with something like 1.12. All right, here's another one for you. Identify the strongest intermolecular force in each of these chemical species. So this is a great time to pause the video, take a look at the electronegativity, actually go through each step to draw out the Lewis dot structure for that molecule, so that way you can better take a look at it. All right, how did you do? So hopefully you were thinking, oh, well, CH3OH is a trigonal, tetrahedral shape. I know that my carbon and hydrogen are sharing their electrons pretty evenly. And so O and H are going to be, O especially is going to be our electron hog here. So that little spot of our molecule is going to be a little bit negative, with the this end of the molecule being a little bit positive. Hopefully you took a look at the OF2, and then of course subtracted to find out the difference in electronegativity. We get 0.5. So it would be a polar molecule. Here's BH3. Of course, that is our octet exception. So I look at my electronegativity difference of 0.1. There's PCl3. And once again, I'm going to look at that shape. That is our trigonal pyramidal. I should have mentioned that this one, the BH3, is trigonal planar. And so which is going to have the strongest intermolecular force? So obviously, my methanol, CH3OH, is going to have the strongest, followed by PCl3, then OF2, then finally BH3. All right, so the steps to solve solution stoichiometry problems are right here. We've already done some of them. So you need to do a couple of more of those. Here we go. So here's a good reaction for you. Now, this is really a tough one. So like I said, you may want to pause the video and see what you can do. All right, so how did we do? Hopefully you first wrote that equation and made sure it was balanced. And then, of course, you started with your moles of the chemical that you know of. Use your mole ratio from your periodic table. Your mole ratio from your equation. And then, of course, you took your moles, multiplied by your, can you see that? Hopefully you can. Divided your moles by your molarity to get the volume in liters, which is what we're asked for. Oh, I am so sorry that this didn't turn out right. So we've got a solution for you, a sulfuric acid, which is reacting with potassium hydroxide. And so there is our answer. So compare that with what you've got. If you have some problems or some questions about these, just let me know, and I will try to help you as best I can. All right. So here is another one, solution stoichiometry. And so hopefully you came up with something like 85.8 milliliters. All right, and here's a real life hospital example using Tris buffer. And so, of course, you're going to use your molarity formula. You can use your triangle. You've got to convert that volume to liters. And hopefully you came up with something sort of like that. And then, of course, I had to do my molar mass where I added up 4 C's, H11, 1 N, and 3 O's. All right, to get that the amount of the mass of the tris buffer that you're going to have to use. And of course, you would dilute that to 500 milliliters. All right. Now, if after I mixed up that 3 molar solution, somebody else in the hospital needed 2.10 solution, we can use our formulas. And it's this one, and it's just the concentration in molarity. You can also do the concentration in any other way, for example, like percent. And hopefully you came up with something that looks like this. Come on. All right, there we go. Rounded to 3 significant figures as well. All right, so what if after, okay, there we go. All right, so there you go, your Unit 3 test. I'm hoping that you're feeling ready. Make sure that you review those gas law formulas and the molarity formula. And then as soon as you're finished the test, start working on Unit 4.